Okay, great. So thank you all for joining. In this session, we have John Baker from IntelliMagic, who'll be sharing his knowledge on zHyperlink. As per usual, if you have any questions, feel free to write them in the chat box as we go along, and John will answer them towards the end of the presentation. Also, I will paste a link where you can leave session feedback as well, and I'll put that in the chat box for you now. And with that said, John, over to you.
Thanks, Piara. Thanks everyone for joining. Hello from Toronto, Canada, across the pond. It's morning here. And I know it's afternoon in the UK, and good day wherever it is, whatever time you're in today. I'm going to talk about zHyperlink. This is kind of an IO session. If you're not an IO expert, don't worry. We're going to give a little bit of a background on how IO works in the Z architecture. So agenda here, a little bit of an overview, traditional versus sync IO. I'm going to talk about sync a lot in context. zHyperlink is sometimes referred to as synchronous, but there are many other contexts in which we use the word synchronous, referring to IO and other things. So we'll set those things straight. Talk a little bit about the hardware, the connectivity, disaster recovery implications that may come into play if this is something that you're looking at. And then the best part, we'll look at some real world results. This technology has been around for a couple of years. I've been studying, and I know many others at IBM and others have been studying it. Our software is updated to show all of the data that can be reported in this space. But up until recently, it's mostly just been test data, lab data. For this presentation, I'm very fortunate. A couple of our customers have generously allowed me to anonymously, of course, share their data where they're running zHyperlink and pretty impressive results. And of course, as Piara said, they have time for your questions at the end. So firstly, just a little bit of a level set, some of the existing IO components. I'm kind of a visual learner. I'm a fan of pictures. So, again, for those of you, if you're not familiar in a general way with IO and Z series environment, on the left, we've got our KEX, our machines, whether those are 14s, 15s, 13s, whichever model you have. You've got your optional FICON directors in the middle. I point those out for now because that's not something you will use with zHyperlink, but we'll elaborate on that. And then on the right, the storage, DS8K, of course, you've got the main storage cache. All data travels through the cache and backend drives. And of course, there's a lot of components, subcomponents within the hardware that I kind of described here. And some of these can be very important in a zHyperlink environment, and some not so much. So we'll kind of contrast those. To get us started a little bit, just going to talk about what I'll call the life of an IO in a typical Z environment. So without going into too much detail, this is not the principles of operations. I wouldn't subject this to you. I wouldn't subject myself to that at 8:30 in the morning. I'm not sure that my brain would be quite ready for it. An application program wants to read or write some stuff. So first it's got to open the data set. It's going to issue the read or write request, hands that off to an access method, part of the operating system. Now, of course, you can technically, you could write your own access method, but it's not generally advised. You need to know where all the pieces are in storage, and that can be a little bit risky. Anyway, the access message will build your channel program, describes the data location and the type of access. And of course, if you're buffering, which hopefully you are, and the data is found in a buffer, it might return right away to your program. If not, hands that off to the IO supervisor. I kind of like to think of iOS as the traffic cop in the IO system, and handles priorities. So you can have an IO priority, which may be separate from your CPU priority. Handles any queuing. This is where IOSQ and PAVs come into play. A little bit of a historical concept in Z, where only one IO at a time ever went to a logical volume. So the IO supervisor was simply saying, well, is this volume in use right now? And if it is, it flips a little bit that says it's in use, and you have to wait, and you would queue. And this would be IOSQ, which simply stands for IO supervisor queue time. PAVs largely resolved that, and you pretty much don't see IOSQ anymore. Eventually, it will issue the start subchannel and hand that off to the channel subsystem hardware. And just to be clear, this is still within the KEC. The channel subsystem is just another area within the machine that is dedicated to handling the I/O. Channels are another set of dedicated processors. System assist processors, SAP, they're also known as. This is going to select a path to the disk subsystem or storage subsystem. Channel is going to execute that channel program that was built back up by the access method and handle that data flow of packets back and forth. This is where you can incur some pen time, another delay type of the different response components. We'll discuss the subcomponents in a moment. So then we move over to the disk subsystem. What happens over here? Everything goes through cache. There's quite a bit of effort that has to take place on the disk subsystem side. First of all, it has to decode the channel program. Of course, architecturally, our stuff is written in what we call Z language. I'll put generically count key data, or CKD. All data that's stored in modern disk subsystems today and has been for several years is stored as fixed block. So first it has to decode and translate that to fixed block. It's got to manage cache and NVS, non-volatile storage. That's a second battery-backed copy of your data. So writes, for example, are written to 2 copies in cache, and then the I/O is marked complete. It's not destaged to the disks yet, but because it's got 2 copies of it, if there were a failure, your data is safe and it'll be destaged later. It has to manage extent integrity. When we think about IOSQ, for example, and eliminating that delay for contention, well, if you think about it, it didn't actually eliminate it. It kind of just passed the buck. So instead of queuing in the channel subsystem and saying, well, this volume is busy right now, you can't update that extent because somebody else is updating that extent. Well, for the basics of data integrity, you still can't update the same extent. You can't have 2 applications updating the same extent at the same time. That would be an exposure. The disk subsystem has to manage that. So your channel program will have a component called a define extent, which says this is the extent, we'll say the range of tracks, for example, that I'm looking at. And am I reading or updating? If I'm updating the same range of tracks as someone else, well, the disk subsystem is going to serialize those requests, make sure they don't go at the same time. So this is something that can still show up. It's very rare. The hardware is really fast nowadays, but if you start to see a little bit of pen time in a device busy, it could depend on which bucket it lands in, but that could be an area there. Initiating staging and destaging, obviously data does need to be fetched from the backend drives in the case of a cache misses. Managing RAID structures, we still got RAID. So even though most people aren't on hard disks or on flash solid state disk nowadays, you'll still very likely have a RAID 5, a RAID 6, maybe a RAID 10 configuration where you've got parity or second copies. Every time something is written and updated on those drives, I got to update those copies and update those parities to keep that in sync again in case there's disaster. Drives break, flash drives break, spinning drives break. They break when an array. The controller needs to be able to reconstruct the data that was there from the data that's left over. That's what RAID does. And lastly, replication, which notice in brackets there, I've got a couple of the response subcomponents that would apply. So replication, disconnect time, and just briefly, what makes that interesting is the disconnect time. Disconnect time is traditionally associated with a read miss. If your data is not found in cache, the channel would quote unquote disconnect. FICON channels don't actually disconnect the way ESCON did, but it'll still mark that time where the channel will do something else while the disk subsystem fetches the data from the backend drives, stages it into its cache, signals the channel, says, hey, I got your stuff, come get it, and it'll reconnect. And during that delay, that'll be disconnect time. Because writes are written to cache, as I said earlier, and immediately marked as done, they traditionally will not incur disconnect time. Now, if you're doing synchronous replication says the IO is not complete until my copy's in the other box, and the other box can be across the floor or 50, 100 kilometers away, for example. And for that case, you will incur disconnect time while that write is being propagated from one controller to the other. Now, bear that in mind. That comes into play as we talk about zHyperlink. Your DRP options are more limited. We'll discuss those. Backend ranks, drives, pools. This is where all the data is. They read and write the data, of course, error checking. Now I won't spend too much time on that because those actually don't apply in the zHyperlink environment. You'll find out why soon. All right, so that was, again, just a kind of a brief overview of the life of an IO. Quite a bit, as you can imagine. IOs are expensive. This is, it's not just using the CPU to do instructions. CPU time is incurred to do IOs, which is why obviously we like to reduce them. So how long does that all take? This is kind of a stacked chart showing you the response times. The way I like to express it, I think it's a good way. I'm using Telemagic Vision here. You can use your favorite tools. It's looking at the subcomponents, and then you can see at the top the total there. So about half a millisecond, 500 microseconds, depending on the unit you like. We will be talking in microseconds later when we talk about zHyperlink, so that's relevant. And that's fairly typical. You can see some numbers down to even 0.2 I've seen, but this is fairly common, and you see that breakdown. Virtually no IOSQ, as I mentioned earlier, largely resolved with PAV, a little bit of pen time, connect time, the traditional productive transfer time, if you will, although there is some protocol involved in that, and disconnect time, which again, for reads, traditionally that's just a read miss, but if you're doing sync replication, you're going to have some disconnect time related to your writes as well. And lastly, a new component, I'll say new in the mainframe world, it's been around a couple of years, interrupt delay time. And that is, in a nutshell, when your IO is complete, it's back from the disk subsystem, it's back from the channel, it's in your channel subsystem in the KEC, and it's actually signaling the LPAR that requested the IO saying, hey, I got your stuff, come get it. And generally that's an instantaneous response. As we can see, there's none of that delay here. If you do see that, and I have seen it in a few data samples, those tend to be small, low weight LPARs, test LPARs, for example, where the machine is just busy. And if they have a very low weight and the other LPARs are taking their share, that LPAR may just not be getting dispatched. So if you do see that, there's no tuning to be done in your IO subsystem. There's no tuning to be done in your channels. That's a dispatch delay component. Okay, let's switch gears a little bit and talk about synchronous IO, or in our case, specifically zHyperlink. So again, your high level process starts the same way. The application program will ask to do a read or write, hand that off to the access method, the IO supervisor. Now there's a component in here, an IO driver called Media Manager. And Media Manager is going to look at your IO and essentially say, are you eligible to use zHyperlink, this new technology? And we'll talk about what eligibility, there's a number of pieces. We got a slide on that coming up. But essentially, if that's the case, then instead of going to the channel subsystem, you get handed off to this PCI board, this card that you plug into the box. You can have about 8 of them plugged into your box, zHyperlink feature. And you will use this dedicated link, PCI Express network component, going straight over the disk subsystem to another similar PCI board. It's essentially a memory-to-memory access. The reference there is CPU waits for PCI DMA operation. As I mentioned, DMA standing for direct memory access. This is kind of the technology that we're using, which is partly what makes it so fast. Literally, the cache in the disk subsystem is talking to what I'll call the cache, main memory, in the KEC, and just moving data directly back and forth. It's not going through the channels. It's not going through the channel subsystem. Those are still there. I mean, this FICON doesn't go away or anything, but if you use this link, it's just going to do the direct IO. Now, another really important aspect of zHyperlink is that your application does not undispatch. So in traditional IO, when you hand things off to the channel subsystem, there's those system assist processor that does the IO. That's a dedicated processor. So your application will get undispatched. It essentially gets swapped out, goes to sleep, while waiting for the IO to be completed by the channel subsystem. And as zHyperlink, you issue your read or write requests and you wait. So you're spinning on the core. Now, this reminds me of the Cheryl Watson paper from a few years ago, where Frank Kind, love Frank, was talking about this concept and saying, wait a minute, you're gonna hold on to the CPU while you do an IO, which takes way longer than doing CPU instructions. And you're gonna do this on purpose? I mean, I totally see Frank's point. It seems conceptually crazy. If you think about it, this concept is actually not new. It's kind of a back to the future. It's kind of a in the very beginning of computers, you did wait. And of course, it took an enormous amount of time compared to the CPU time to do an IO. And as technology improved, we kind of separated those, decoupled them, if you want to think about it that way, saying, I'm going to do this IO, I'm going to have the CPU not wait, I'll signal the CPU when I'm done and pick it up again. But because IO has improved so much, this has really become a possibility. And the last point I'll just mention here, the processor cache content is preserved. I'm sure you've been to many sessions at this conference and others, and your IBM and other reps talking to you about processor cache. My colleague Todd Havikas gave a session this week on processor cache. You hear concepts about the nest, relative nest intensity, level 1 cache misses. You know, if you're not familiar with what these things mean, at a high level, what we're talking about is the local caches that each CPU has. Each CPU has its own dedicated level 1 and level 2 cache. These are very fast. This is where your next instruction comes from. And if it's not there, well, then I got to get it from level 2. And it's not there, I got to get it from level 3 or level 4. And those are further out, literally further to go. And when you're talking about a processor that is cycling at 5.2 billion cycles per second, every cycle waiting to fetch something from a higher level cache takes longer. And if you've been to a Dave Hutton session, he'll tell you that, you know, the days of these huge increases in processor speed are gone. Moore's law is setting. That sun is setting on us. So we've noticed already, you don't see these big clock increases. Today's clock speed of a Z15 is no faster than the Z196. It's like an N minus $5. Now, of course, it does way more work, but it does way more work because of the intelligence. Essentially, the speed that you can get the data to the CPU is far more important than the CPU speed itself now. So all that to say that now, if you think about it, it can be worth it in some situations to hold the CPU. Your instructions are loaded up in those local caches for your application. That means they're still going to be there because you're just going to pause, do this IO, and then resume. In a traditional IO, when you get undispatched, another application is very likely going to use that processor and is going to, of course, flush your cache lines and load up their cache lines. And when you get dispatched again, well, your stuff's not going to there anymore. You got to load it up. That's a whole lot of time, a whole lot of overhead, a whole lot of CPU overhead that should be considered. So that's why this option is now something to look at. More directly, the actual response time. So this chart, the blue line is the same response time chart that I showed a few slides back, just not breaking down the components, the pen, connect, disconnect, and so on, just showing the total. So you can see, you know, half a millisecond, roughly down the middle of the chart is where it was. I've changed the scale here, notice on the left, to microseconds. Same number, just change the scale to represent what we're talking about here. So 500 or so microseconds. The zHyperlink response at the bottom of the screen there indicated it's about 20. This is what's been advertised by IBM for quite some time. And I can tell you from looking at a lot of the data, it's pretty accurate. That's what they're getting. Very, very impressive. Think about that. I mean, literally more than 10 times a difference. So let's talk a little bit about the operation. You may have seen this slide before if you've looked at some zHyperlink technology. Again, not considering all of the pieces here, but kind of a high-level process. That IO driver at the top, that's the media manager that I mentioned earlier, the guy that decides, okay, are you eligible? There's that first question. Are you sync IO eligible? If not, you go to what we call heritage IO. You go to the channel subsystem and FICON takes care of you. If you are, You get passed off to that board, and you get sent directly to the disk subsystem through that dedicated PCI interface, as I described. Now, notice that third step, when conditions do not allow synchronous execution. Well, what does that mean? Conditions do not allow. I can tell you that the vast majority of those conditions are simply that the data was not found in the disk subsystem cache. If it's not there, there's no way that you want to hold a CPU. 20 microseconds is one thing. That's what we're talking about roughly, that you would literally, your application is spinning on the CPU. If you have a cache miss, even to a flash drive, that could take a millisecond or two to be staged and then reconnected in a traditional sense. I mean, that's 1,000 microseconds. That's just too long. You're not going to wait that long. So it's going to come back. It's going to say it wasn't in cache, or again, the conditions were not allowable. And it's just going to hand it off to the what's labeled here, that heritage IO, to the channel subsystem. Do traditional IO, and your application will undispatch at that point, but you'll still get your data. It'll just take a little bit longer. I would point out, though, it's always, not always, but it's generally worth trying. So an interesting point about zHyperlink is, well, does it know that the data is in cache? No, it doesn't. It has no way of knowing whether data is going to be found in disk subsystem cache or not. But it's still worth trying, because what happens if it gets to the disk subsystem, the data is not in cache, it says, okay, goes back and drives the IO traditionally. However, because the request did arrive at the disk subsystem, well, what's it going to do? The DSAK is going to say, oh, I had a request for this. I'm going to go get it. It's going to start the staging process while you're going back and driving your IO traditionally. So by the time your IO gets there through your traditional channel, there's a reasonable chance it might be in cache now, or at least it's not going to take as long because the staging operation has started. Lastly, just important point, again, at the bottom, to emphasize that this technology is not replacing Vicon. As the title of the session suggests, this is a fast lane. This is for certain types of data. You have this fast lane option. Vicon is still there to do most of the heavy lifting for most of your IO. Okay, let's switch gears a little bit and talk about sync versus sync. Yes, we've talked about sync IO and a zHyperlink context. If you think about DB2, now if you're a DB2 person, DB2 people, yeah, I know what sync IO is. Sync IO is bad. Sync IO is when my data wasn't found in my brain is dying on me here, in the DB2 buffer pools, excuse me. And my DB2 transaction, if you will, had to wait to do a physical IO. This is very, very expensive. Very much the way we're talking about was zHyperlink, except it's traditional IO. It's a really long time. So in a DB2 world, you really want to minimize these sync IOs. Of course, in zHyperlink, well, it's going to be 10 times faster than a traditional IO, so you want to maximize these things. So, making the best of a bad situation is turning this bad sync IO into a good zHyperlink IO. Essentially, if you have to do the IO anyway, because it wasn't found in a buffer pool, which would be faster. Buffer pools are in main memory locally or in your coupling facility, which we're going to talk about next, which would still be faster. But if it's not in one of those places, better to do a 20 microsecond IO than a traditional IO. So speaking of coupling facilities also use the concept of sync. Well, they talk about sync versus async coupling facility requests. And here the concept is actually a little bit closer. So the point at the bottom there, if you're familiar with sync versus async coupling facility and how that works, this will help in your understanding of zHyperlink, because the concepts are very similar. Sync being that I'm holding the CPU waiting for this request because I expect this request to be very fast. In a coupling facility context, we listed here 5 to 8 microseconds. zHyperlink, maybe 20, but still, it's a lot faster than our traditional IO, and the CPU does spin or hold onto the application. But again, the benefit of that is when your IO is complete, or your sync request, we'll call is complete, There's no on dispatch, there's no getting back into dispatcher queue, there's no reloading of the cache lines, you just resume very, very fast. Okay, a little bit on the hardware. I did mention the PCI link. You have to have at least 2 zHyperlinks. These are an 8 gigabyte per second optical link direct connect. So notice at the bottom here, I've got my traditional FICON links that go through my optional FICON director. You don't have to use FICON directors, but most people do. But to be clear, with zHyperlink, you cannot use directors for these connections. They must be a direct connection from the KEC, which must be a Z14 or later, and the DS8K using this unique interface. I believe it's actually similar hardware. The interface itself, I believe, is very similar. I'm not 100% certain, but I believe it's very similar to a coupling facility connection. So you do have this limited distance of 150 meters, point to point, no directors, not channel. So what does that mean? Now, thinking about that distance, 150 meters apart, maximum. Well, I mentioned synchronous remote copy previously. Many shops may have implemented a synchronous remote copy environment, which means I have a secondary disk subsystem that might be more than 150 meters away. Does that mean I can't do this? That's right. It means I can't do this. You can't do writes anyway. Technically, you could do a read. You could enable zHyperlink for reads to the local box because I don't need to involve the secondary, but I couldn't do writes at any kind of distance. So something to consider. Just specifically to look at writes for a second, if you do want to enable that, originally when zHyperlink came out, it only did reads. Now it does do writes as well. And it's a really good idea because DB2 logs come to mind as a good candidate for that. If you're not familiar with zHyperWrite, that is a prerequisite. Without getting into that too much, essentially it's a separate connection directly from the KEC to the secondary box. In a traditional synchronous remote copy setup, you go from controller to controller. zHyperWrite says I got a connection to my primary and my secondary directly, so I can do those at the same time. And that is, again, a prerequisite for zHyperlink. However, again, don't forget that distance. You can't just enable zHyperWrite, across the miles. They do need to be within 150 meters. They got to be on the same floor, essentially. So the point being here, your replication approach, if you want to look at this technology, might need to be reevaluated. Just briefly, I mentioned a possible read-only approach. This technically would work if you only want to enable zHyperlink for reads, and you can optionally do that, and that would help. However, you couldn't do writes, and again, personally, I wouldn't recommend that because one of the big beneficiaries is going to be DB2 logs, and that's a write. So really, this is kind of a choice. You can always do async further away, but you can't do synchronous unless the boxes are on the same floor. Just something to consider. Okay, let's talk about enablement, eligibility. And as it says here at the top, thank you, John Berg from IBM. He shared this slide for me from the Washington System Center. I've not altered it in any way because I really think this covers all of the eligibility aspects perfectly without me kind of twisting it into my own words. I'm not going to go through every point on here, in detail, but essentially what we're talking about is we're talking about DB2. That's the primary and initial candidate that this was designed for. And if you have the right level of DB2 and all of the APARs, and you've got at least a Z14 or later, and you've got a DS8K, you should be able to do this. Also some VSAM. Now VSAM, we'll talk about these different types, but there you've got to enable that through SMS. DB2, it's kind of smart. It knows what DB2 IOs are eligible and what are not. So it'll take care of itself. But with VSAM, you need to decide which storage classes do you want to enable. I will just point out one aspect that I've seen in the field, as something that appeared to be enabled and didn't work. And that's the 4K block size mentioned down in the middle there. That's a current requirement. And I have seen storage classes that were enabled, for example, and the customer to assumed that, well, this should work. Why isn't it using zHyperlink? And it was because the block size was greater than 4K. So that would not go through. All right, for the sake of time, let's look at some data. So tracking this eligibility. Now, this is, again, IntelliMagic Vision chart. You can do this yourself. This is breaking down the data types using SMF42 data. There's excellent statistics within SMF. Thank you very much to IBM 74 subtype 9. The PCI record will give you information from the card perspective, including the traffic and the response time on the cards. You can verify that 20 microseconds. The 74s by volume will give you SMS information about sync requests and failures and response times and good stuff like that. And the 42s, I think, are the most detailed ones because this is at a data set level. And again, what we're showing here is rolled up by data set type. And this you can see beforehand. You don't have to be running zHyperlink in order to see what's eligible, which can be really nice. You know, find out how much I can benefit, try before you buy kind of thing. And you can see in this chart by type, you know, read hits and misses not eligible, the red and blue at the bottom, write request not eligible, and then you've got some green and blue. The light green and light blue are eligible. So in the second columns, KSDS data, KSDS index, you know what those are? Those are VSAM, right? But the far left one, of course, linear data sets, well, that's DB2. What's the purple? The purple is synchronous read IO successes. This environment is using zHyperlink right now. A sync IO read success says I used the interface and it worked. Well, how cool is that? It's not just theory. Let's show you some of that data. Again, just going down the line though, lots of VSAM, not so much on the flat files, VDV, DS, VTalk, stuff like that, not really eligible. But you can see the KSDS, which is nice, some entry sequenced, even a little bit of RRDS at the end. But look at your data, see how much of it is eligible for this. Okay, so this is an environment that's turned on a VSAM storage class. And what I'm showing here, the red is the native FICON IO rate. So clearly the vast majority of the IO is still using traditional FICON, and that light gray line superimposed across the top is that response time noted on the right, again in microseconds, so 200 or so, which is about as good as it gets in a traditional channel environment. Then those little blue blips at the bottom, those are successful sync IO read requests. So from this data, and you can see this very tiny at the bottom, that zHyperlink response as advertised right in there around 20 microseconds. Now the percentage of sync content, so that is to say of the total IO, how much of this is using zHyperlink? Not very much in this example, 3-4%. So that's kind of representative of those few little blue blips that you saw. Now, if I just look at that individual storage class, I can get a clearer picture of the actual magnitude, and it's pretty good. You know, what I've got at the bottom in red is the IO rate for this storage class, and labeled as IO rate says it's not using zHyperlink. And then the blue, successful synchronous IO read requests. So you can see that I've many thousands of IOs compared to maybe a couple of hundred IOs per second traditionally. And then during those peaks there, many thousands are using the new interface. And again, when I contrast the response times in yellow, that's just connect time. I took out the other components of response time. If you think about it, you know, zHyperlink response is really just connect. It doesn't use those same concepts, IOS queue pend, it doesn't have an IO supervisor, it doesn't go through those. It's really just transferring data. So if you want to have a closer apples to apples comparison, you could compare that to your connect time. As you can see, it's still substantially better. But one of the nicest samples is this before and after, and this is a DB2. This particular site, this is not a production environment. It is development, but as you can see, the patterns are fairly steady and they're not small. It does repeat very similar workloads on a daily basis. So this was last April on the left is the before picture, and on the right is the after picture in June when they'd enabled zHyperlink. So you can kind of see again, the red is all that traditional I/O, and it's all on the left. Of course, there was no hyperlink in that. On the right, now I start to see this blue successful synchronous I/O read requests. And if you look closely a little bit there, let me just see if I can use this little zoom feature. Well, isn't that cool? I can zoom in and I can see the little bits of green. So those are a few of the requests that failed, that the data was not found in cache, and that can occur. But it doesn't mean, as I described earlier, that it wasn't worth it to make that request. If we look at the percentage of content that in this environment, a little higher, 6-7% compared to all I/O. But again, let's zoom in a little bit. If I go to the type 42 records and my detailed stats, I can see all of the eligibility as well by different type reads versus writes, and what was successful. It's the purple on the right that's successful. I'm going to clean this up a little bit. I'm going to remove a bunch of the other variables to make this clearer in this before and after picture, because in this environment they had only enabled reads. So I take the writes out of the picture and take the requests that were not eligible out of the picture. And now what I have is a very nice view. On the left is all the data that was eligible, and on the right is what used zHyperlink. And again, while the patterns aren't perfect, you can see that they're reasonably close, and that most of the data that was eligible is actually using it. And I'm going to focus a little bit on this this spike at the far right. We'll get to that in a moment, but just bear in mind, you can see there that it's a substantial portion of the original area that was eligible, the highest area, and that it did use it. But just briefly, one other area of measurement that I would recommend you look at. If you're not familiar with a locate record instruction is an I/O. If you're not familiar with it, when we think about I/O rate in mainframe environment, traditionally what that's referring to is the start subchannel rate. This is measured at the channel level, at the LPAR level. So this is your RMF74 subtype 1, which is the logical volume, and it's taken from the perspective of each LPAR's view of that volume, where it's saying how many I/Os did I did, and what was the response time, or more specifically, what was the I/Os queue, pen, connect, disconnect. That's all well and good. Another record is what we call sometimes the cache statistics, is 74 subtype 5, and those are reported from the perspective of the storage controller, not from the perspective of the LPAR, and those report in locate records. Why are they particularly useful and relevant here? John asks the rhetorical question. I'll tell you why. Because as we've shown up till now, your traditional I/O rate and your zHyperlink are reported completely differently. I've got that traditional I/O rate value, and then I've got the sync request I/O. They are independent because, again, from LPAR perspective, zHyperlink is not using the channel subsystem. It's not using channels, so I can't measure those together. Locate record within the controller, the controller says, I don't really care what LPAR this came from. I'm just counting all the I/Os that I'm managing within my box. So it includes everything. So whether the I/O request, whether it's a traditional that came from a channel or a zHyperlink, they're all counted together. In other words, my locate record rate is a true measure of all of my I/Os, both the synchronous and the non-synchronous, I'll call them in this case, traditional. So what I've got superimposed here is my locate record rate plotted on the left side there. If I look at this big spike on the right that I indicated, you can see about 19,000 locate records. No, excuse me, that's the I/O content. You can see that's up about 75%. The red line, excuse me, about 14,000 I/Os per second. And the successful synchronous I/O read request, which is blue underneath it, was 10,000. So, a lot, like 2/3 or more, 3/4 of these IOs, of my total IOs, were using zHyperlink in during this particular very interesting peak. I mean, it's good throughout, but this gives me a real nice apples to apples comparison. Now, what can I do with that? Well, our smart developers said, hey, well, one thing I can do is I can give a weighted response. So because I know the total IO rate and the response time for the traditional IOs and the response time for zHyperlink IOs, I can say, what's my overall weighted response for all IOs? So the response time in green here is that's the traditional original response time. It looks like around during that peak around 0.7 milliseconds plotted on the right-hand axis. And then underneath that, this yellow lower values that's labeled average response time for all IOs. That's our weighted response time that's factoring in the response time, which we know the 20 microseconds. I didn't put it on here to try and not clutter too much. The 20 microseconds for Hyperlink versus the 0.7 or so traditional. And again, waiting for how many IOs were done in each flavor gives me an average response time for all IOs of about 0.2. This is a quantifiable value that you can present. You can say that here is the direct benefit to my average response for this application, because the application doesn't know or care whether it used traditional or sync IO. It just wants to know how long it's taking. And it knows that on average, by enabling this technology, it's only taking 0.2 milliseconds versus 0.7. That's a substantial improvement in the overall IO response time. Now, if I take this further, I can look at the DB2 perspective. We've traditionally just so far been looking mostly at RMF values, type 42 records, but for a DB2 database, I can say, well, what are the read and write IOs? What are the sync requests? It's the same statistics, but I can align those with my type 42s to get some of these measurement values. Specifically what I'm talking about here, let me just go to the next slide, is the DB2 trace records. So if you're a DB2 person, you're probably familiar with these. These are the SMF 101 accounting records. They are, to put it mildly, massive compared to RMF and generally unwieldy. We process these within our tools. I suppose you could probably try and write something, but it might be painful. But this is the same data that I just showed those IO statistics previously. Now, I'm not a DB2 expert, but Jeff Berger is a DB2 expert. He's on our team, and one of the things he tells me DB2 people don't like is synchronous IO wait time. And go back to where I described the sync versus sync earlier when we were talking about DB2, we were talking about coupling facilities. So a DB2 sync IO wait is where I have to do this physical IO where the DB2 transaction is in flight. So what I'm measuring here is the commits, that the red line, solid red line in both is the number of commits. And then the stacked bar of those components are the different transaction response components in DB2 language, milliseconds per commit. People have the nerve to phone me when I'm talking. You can see that there's DB2 class 2 CPU time at the top, but the largest component on the left, that yellow, is the database synchronous IO wait. And this is, again, the same data before and after. You can see that basically disappears in the after picture using zHyperlink. You don't have to be a DB2 expert to look at this and say, wow, that's a whole lot better. And to make it clearer, if I eliminate the other components and just say, what was my database synchronous IO wait time, milliseconds per commit, which is on the right-hand axis here. It's like 100 and, no, excuse me, left side axis, I was wrong. About 50 milliseconds per commit down to about 20, or no, down to about 6. I keep mixing up the two axes. I mean, it's literally day and night. And that is quite often, as was in this example, the largest component of a DB2 transaction. This is in a nutshell why DB2 folks really, really like this. They don't maybe necessarily, I'm a general performance guy. They don't care about workload manager and hardware and hypervisors and things like that we might care about, processor polarity, but they do know that, hey, this is how long my transactions are take, and this is a huge, huge benefit for these guys, and a measurable benefit if you look at all the statistics. And no, I don't work for IBM, and IBM isn't paying me. I just think this is cool technology. Okay, so in summary, I/O is all relative. I think really, if you think about it, everything's an I/O conceptually. Getting something out of your level 1 cache in your processor, it's technically an I/O. I'm reading or I'm moving data. It doesn't have to be from a traditional disk to be considered an I/O. So these are the approximate times to fetch data in microseconds from a local buffer, coupling facility, zHyperlink, Ficon, and all the way down. So if you thought of this, if your local buffer took a second by way of comparison, this gives you kind of a relative idea. So your sync coupling facility request is 8 seconds. So that, that still wins. But now next in line, I've got this new option. I've got this 20-second option using zHyperlink. If I did a traditional I/O and I get a Ficon cache hit, that's 2.5 minutes. By comparison, 2.5 minutes. That is about the fastest that you can do an I/O. And literally, I can say that's right from looking at real data. On the left there, 150 microseconds. That's about it. That's, I don't have really any IOSQ or pend or disconnect. The channel wasn't busy. I went straight to the controller and my data was right there in cache, and I got back as fast as possible. That's just as fast as you can do it with all that overhead. And then remember the dispatch time. I got undispatched in order to do that I/O. So it's not just comparing 150 mics to 20. It's then I have to get in line. I have to get dispatched again. Now, if I'm DB2, I'm going to be near top of the food chain. So I'm going to get dispatched pretty quick, which is all the more reason to consider, well, maybe it's okay for DB2 to be holding the processor, because that is a consideration for a lower priority work. Do you want that holding onto the processor for 20 microseconds to do its I/O? And down on, you can see, even if you're using flash, as most people are, a backend miss is still exponentially longer. And of course, the tiered backend is if you've still got some spinning disk. And I believe I'm up against my time. A few sources here: the original paper written by a number of smart folks in Poughkeepsie there, the Journal of Research and Development. Again, this came out a couple of years ago. Our own Dr. Gilbert Houtskammer's white paper on the holy grail of mainframe I/O. Frank's write-up in Cheryl's tuning letter, that's really good. It's good too. There's a lot of good detail in there, and love Frank's knowledge as well as his sense of humor. Thanks again to John Berg for his content. And if there's still time, I'm happy to take questions. Not sure if I do have time. Am I over?
Yep. Any question, guys, feel free to leave it in the chat box, or if you want to speak in person, let me know and I can unmute you.
I might. I don't know if it's saying there, Pierre, I might not have the right screen.
Yeah, no, there's nothing coming through at the moment.
Okay, so I'm not saying good.
But thank you so much for your presentation. Really appreciate your time, John. That was really insightful.
Cool. Yeah, my pleasure. Okay. Well, again, thanks everyone then, and don't forget to submit your reviews. And again, don't forget the excellent charity work. Always really appreciate the work that GSE UK does. It's one of my favorite conferences. I know it's not the same as being across the pond, but I do really enjoy being part of this group. It's good content this year. Thank you, Piara and Mark Wilson, and everybody else over there, and stay safe, everyone.
Brilliant. Thanks, John, and thanks everyone for attending.